Number 6. The Venus Table. The Maya were obsessed with Venus in a way that European astronomy did not catch up to for over 1,000 years. The Dresden Codex, one of only 4 Maya books to survive the systematic burning of Maya literature by Spanish missionaries in the 16th century, contains a Venus table covering pages 24 and 46 through 50. This table tracks the complete synodic cycle of Venus, its 584-day journey through 4 distinct phases: morning star, superior conjunction when it disappears behind the sun, evening star, and inferior conjunction when it disappears again. The Maya track this cycle across a 5-year period, during which Venus completes 5 complete synodic cycles, while Earth completes 8 solar years, a relationship that produces a near-perfect mathematical alignment that the Maya identified and documented. Their calculated value for the Venus synodic period was 583.92 days. The modern measured value is 583.92 days. The Maya calculated this figure by observing Venus over extended periods, tracking its first appearance as morning star against a fixed horizon marker, and accumulating observations across enough cycles to average out the natural variation in the planet's behavior. The precision they achieved to within fractions of a day over a 5-year cycle required sustained, systematic observation across generations, recorded and transmitted with enough fidelity to allow the calculation to be refined rather than restarted with each new observer. They also used this calculation for military strategy. Maya kings timed military campaigns to coincide with Venus's first appearance as the morning star, a practice documented in hieroglyphic inscriptions at multiple sites. The astronomical calculation was not abstract knowledge. It was operational intelligence, used to schedule warfare at cosmologically sanctioned moments. European astronomers did not achieve a comparable precision for Venus's synodic period until Tycho Brahe's systematic observational program in the 16th century, approximately 1,000 years after the Maya table was compiled. Number 5. The Eclipse Prediction Table. The Dresden Codex contains an eclipse prediction table that a study published in Science Advances in October 2024 by anthropologists Dr. John Justison and Dr. Justin Lowry of the State University of New York determined was accurate enough to predict every solar eclipse visible from Maya territory for approximately 700 years. Not approximate predictions. Modern modeling indicates that this method maintained predictions within 51 minutes of accuracy over 134 years. The mechanism the Maya used was not a simple cycle repetition. Instead of using a single cycle and starting over each time, Maya calculations used a cumulative approach, overlapping tables that allowed them to gradually correct for tiny errors caused by the natural drift of astronomical cycles. The table covered 405 successive lunar months. When the table reached its end, Maya calendar specialists called daykeepers did not simply restart from the beginning. They reset the next table to intervals of 223 or 358 months, both of which represent eclipse cycles, carrying forward the accumulated precision rather than losing it. The evidence dates back to around 550 CE, meaning the Maya were actively predicting eclipses 1,000 years before European astronomers formalized lunar node theory. The significance of this cannot be overstated. Predicting solar eclipses requires understanding the relationship between the Moon's orbital plane and Earth's orbital plane, the lunar nodes, the points where these two planes intersect. An eclipse can only occur when the Moon is near a node at the time of a new or full moon. European astronomy did not formally understand and systematize lunar node theory until the 17th century. The Maya were using the functional equivalent of this understanding to make accurate eclipse predictions 1,000 years earlier, without knowing why the mathematics worked, knowing only that it did, and refining it over generations until it worked reliably across centuries. By demonstrating that the Maya could predict eclipses with precision rivaling that of modern astronomers, the study redefines how Maya science is understood. Number 4. The Long Count Calendar. The Maya Long Count Calendar is the most precise time measurement system developed by any pre-industrial civilization on Earth. The calendar tracks time from a fixed starting point, the Maya creation date, equivalent to approximately 3114 BC, using a vigesimal, or base 20, positional number system that can express any date within a cycle of approximately 5,125 years. The cycle contains over 1.8 billion days. Every single day within that cycle has a unique numerical designation. For context, the Julian calendar that Europe used until the 16th century accumulated an error of approximately 11 minutes per year. Over the centuries that the Julian calendar was in use, this error had produced a discrepancy of approximately 10 days between the calendar and the actual astronomical year. The correction, the switch to the Gregorian calendar in 1582, was controversial, required papal authority to implement, and still required European populations to simply skip 10 days in October to realign with the solar year. The Maya did not have this problem. Their calendar incorporated a correction mechanism, the correlation between the 365-day Hab civil calendar, the 260-day Tzolk'in sacred calendar, and the long count, that kept the system aligned with astronomical reality over extended periods without requiring periodic corrections. The combination of the Hab and Tzolk'in cycles produces a calendar round of approximately 52 years, within which every day has a unique combination designation. The long count extends this uniqueness across 5,000 years. The Maya calendar system did not drift. It did not accumulate error in the way that European calendar systems did. It was designed from a mathematical foundation that is more sophisticated than the Gregorian calendar that Western civilization still uses today. The Gregorian calendar itself being a correction of a correction of a correction of the original Roman calendar, each iteration attempting to fix the inaccuracies introduced by the previous one. Number 3. The Mars cycle. Mars is the most difficult of the visible planets to track accurately because its orbit is significantly elliptical. It moves at different speeds at different points in its orbit, and because its retrograde motion, the apparent backward movement it produces when Earth overtakes it in its orbit, is unpredictable in duration and extent. The Maya tracked Mars systematically across decades of observation and developed a table found in the Grolier Codex, one of the 4 surviving Maya manuscripts that accurately predicted the planet's synodic cycle. The time it takes Mars to return to the same position relative to Earth and Sunday. The modern measured synodic period of Mars is 779.94 days. The Maya calculated value was approximately 780 days, an accuracy of better than 0.01% over a nearly 800-day cycle, achieved with naked-eye observation from fixed horizon markers and multi-generational record-keeping. European astronomy could not match this precision for Mars until Johannes Kepler's work in the early 17th century, specifically his discovery of elliptical orbits, which explained why Mars behaved differently from what circular orbit models predicted. Kepler's breakthrough came in 1609. The Maya had functional predictive accuracy for the same planet approximately 1,000 years earlier, achieved not through understanding why Mars behaved as it did, but through accumulating enough observations to describe the behavior accurately, regardless of the underlying cause. The distinction is important. The Maya astronomical achievement was empirical rather than theoretical. It was built on observation rather than model. But the predictive accuracy it produced was, for practical purposes, equivalent to the predictive accuracy of the theoretical model that Europe eventually developed. A calculation that tells you where Mars will be in 800 days is equally useful whether you understand why it will be there or not. Number 2. The solar year calculation. The Maya solar year calculation, the length of the year, as measured by the time it takes Earth to complete one orbit of the Sun, is more accurate than the Julian calendar that Europe used for 15 centuries. The Maya Hab calendar has 365 days. It does not have a leap year mechanism in its basic structure. But the Maya were aware that the actual solar year is longer than 365 days. They simply handled this discrepancy differently from the European calendar tradition. Through the correlation of the Hab and the long count, and through astronomical observation records that tracked the accumulated drift between the civil calendar and the observed solstices and equinoxes over extended periods, Maya calendar specialists maintained a working value for the length of the solar year. The value encoded in Maya astronomical records determined by scholars analyzing the correlation between long count dates and observed astronomical events is 365.242 days. The modern measured value is 365.24219 days. The Julian calendar's year was 365.25 days, a discrepancy of approximately 11 minutes per year that accumulated to 10 days by the 16th century. The Gregorian calendar corrects this to 365.2425 days, closer to the actual value, but still less precise than the Maya figure. The Maya solar year calculation is more accurate than the Gregorian calendar by approximately 0.0002 days per year. This is a smaller error than the correction the entire Gregorian reform was implemented to address. Europe reformed its entire calendar system in the 16th century to achieve a level of precision the Maya had already reached, by a different route, several centuries earlier. Number 1. The lunar month calculation. The most precise of all Maya astronomical calculations, and the one that most dramatically demonstrates the sophistication of their observational system, is their calculation of the synodic lunar month, the time it takes the moon to return to the same phase as seen from Earth. The Dresden Codex lunar table covers 405 successive lunar months and was maintained with a precision that modern analysis has confirmed keeps eclipse predictions accurate to within 51 minutes over a century and 34 years of operation. But embedded within this table is a specific numerical value for the length of the lunar month itself that is extraordinary. The Maya value for the synodic lunar month was 29 days, 12 hours, 44 minutes, and approximately 3 seconds. The modern laser-measured value, determined using atomic clocks and retroreflectors placed on the moon by the Apollo missions, is 29 days, 12 hours, 44 minutes, and 2.87 seconds. The Maya were off by less than 3 seconds per month, a calculation made with naked-eye observation from stone platforms in a tropical jungle, without telescopes, without mechanical timekeeping beyond the observation of shadow and star position, and without any mathematical tradition that had been exposed to Greek, Islamic, or European astronomical theory. They achieved this precision through the same mechanism they used for all their calculations: systematic observation, multi-generational record-keeping, and the mathematical sophistication to average accumulated observations in ways that cancel out individual errors. Any single observation of the lunar month is subject to observational error. Hundreds of observations across decades, carefully recorded and mathematically processed, produce a value that converges on the true figure with increasing accuracy as more data is added. The Maya did not discover the length of the lunar month. They measured it with an accuracy that the best European astronomy did not match until the work of Johann Tobias Mayer in 1753, approximately 1,000 years after the Maya had already done it. Mayer used telescopes, mechanical clocks, and a mathematical framework built on Newton's theory of universal gravitation. The Maya used their eyes, their stone observatories, and mathematics that European scholars would not understand until they translated the Dresden Codex in the 19th century. The lunar month they calculated, to within 3 seconds, is the same lunar month that the Apollo astronauts measured with laser-ranging equipment in 1969. 1,000 years, 3 seconds, naked eye. 6 calculations, all of them Maya, all of them more accurate than European astronomy for the periods during which they were developed. The Venus synodic period to 5 decimal places. 700 years of accurate eclipse prediction. A long count calendar that does not drift. The Mars cycle accurate to better than 1/100%. A solar year calculation more precise than the Gregorian calendar that Europe implemented to fix its own inaccuracies. And a lunar month calculation accurate to 3 seconds, achieved with the naked eye, 1,000 years before Europe matched it with telescopes and Newtonian physics. Maya astronomical achievements demonstrate that sophisticated mathematical astronomy is not dependent on the Greek and European intellectual tradition. The Greek and European intellectual tradition is the one that was taught in the schools that replaced the Maya schools. The Maya schools were burned, the books were burned, the teachers were in many cases killed. What survived is the Dresden Codex, one of 4 books out of thousands sitting in the Saxon State Library in Dresden, Germany, where it has been since 1739. It has been studied for 2 centuries. Every decade, someone publishes a new analysis and discovers it is more sophisticated than the previous analysis understood. The most recent study, published in Science Advances in October 2024, determined that the eclipse table is more accurate over longer periods than anyone had previously calculated. They are still finding out how good it was.